Right now, while you are getting comfortable, a machine built before most of us were born is whispering to the Earth from the far side of the dark. The whisper takes almost a full day to arrive. 23.5 hours, travelling at the speed of light, across about 15 billion miles of nothing. When it reaches us, it is fainter than almost anything we know how to hear, and we still listen every day with dishes the size of buildings, because there is nothing else like it. Voyager 1 is the most distant thing human beings have ever made. It left in 1977. It is still out there. It is still talking. And here is the part of the story most people have never heard. Out at the edge of the solar system, where the sun's breath finally fails against the deeper ocean between the stars, this spacecraft heard something, not with a microphone. Space carries no ordinary sound, but with two long, thin antennas trailing behind it like whiskers, it caught something real, something that rose, and grew louder, and then settled into a tone that has not stopped since. Tonight we follow it the whole way out, the lucky alignment that launched it, the giant worlds it passed, the picture it turned around to take, the one that made its cameras worth losing, and the sound waiting for it past the boundary which is not what anyone expected. If these slow journeys help you rest, subscribing is the easiest way to drift out with us again. Settle in. We begin in a summer that comes once every 176 years. Every great journey begins with a door that happens to be open. In the late 1960s, a young engineer doing orbital calculations noticed something that would not come again in his lifetime. The outer planets, Jupiter, Saturn, Uranus and Neptune, were slowly drifting into a rare arrangement. For a few short years at the end of the 1970s, they would be lined up along a curve, in such a way that a single spacecraft could fall past one and be thrown onward to the next, gathering speed at each pass, like a stone skipped across the solar system. The arrangement happens roughly once every 176 years. The last time the planets had stood this way, Thomas Jefferson was alive, and the fastest thing humanity owned was a sailing ship. So the door was open, and it was closing. NASA built two travellers for that door. They were nearly identical twins, each about the size of a small car, each carrying 10 kinds of scientific instruments, a large white dish antenna shaped like an upturned umbrella, and 3 quiet generators that made electricity not from sunlight, which would soon grow too weak, but from the steady warmth of decaying plutonium, power that asked for no sun, power with a slow known ending built into it from the first day. We will come back to that ending. The mission was named Voyager. Here is a small detail that confuses everyone, and that you can carry with you tonight as a piece of quiet trivia. It left Earth on the 20th of August, 1977, from Cape Canaveral in Florida, riding a Titan Centaur rocket. Voyager 1 followed 16 days later, on the 5th of September. The numbers were not about who left first. They were about who would arrive first. Voyager 1 flew the faster, tighter path, and that December it quietly overtook its twin in the dark beyond the asteroid belt. And from then on it has led the way for the rest of human history. Think for a moment about what 1977 was. The rocket that lifted Voyager carried a computer with less memory than a single photograph on, a modern phone. The engineers who built it used slide rules alongside their early computers. Many of them were young, in their 20s and 30s, and some of them are still on the mission today, grown old beside their machine. Because Voyager has now flown for very close to 50 years, and a project that long does not change hands easily, it becomes something closer to a family. The two spacecraft climbed away from Earth in the late summer of 1977, and Earth became a small blue coin behind them, and then a point, and then just one light among the others. There is a kind of peace in how slowly the journey unfolded from there. Space stories are usually told as moments: launches, landings, sudden discoveries. But the truth of deep space travel is long, calm patience. It took Voyager 1 a year and a half just to reach Jupiter. 18 months of coasting through silence, instruments humming, signals home growing gradually fainter, the sun behind it shrinking by slow degrees. The spacecraft did not burn engines all the way. It simply fell the whole time. Along the curve the engineers had drawn for it years before, the curve through the open door. And while it fell, it listened and measured and waited. The machine never sleeps, but it is very good at waiting. It has spent most of its life waiting, in the dark between worlds, with nothing nearby for hundreds of millions of miles. If you have ever lain awake at night feeling far from everything, you have felt a faint shadow of Voyager's whole existence. The difference is that Voyager was built for it. The loneliness is the job. 2 more travellers were already out ahead of it, Pioneer 10 and Pioneer 11. Smaller scouts launched a few years earlier. For 2 decades, Pioneer 10 would hold the record as the farthest human object. Voyager 1 was patient about that too. We will see much later tonight the exact winter day in 1998 when it quietly passed Pioneer in the dark, with no one aboard either craft to mark the moment, and became the farthest thing we have ever sent, a title it will likely hold for centuries. But that is far ahead of us. In the early months of 1979, after a year and a half of falling, something began to grow in Voyager's forward cameras. At first it was just a bright point that refused to stay a point. Then a disk, swirling enormity that swallowed more and more of the sky, attended by 4 bright sparks of light that resolved week by week into worlds of their own. The largest planet in the solar system was rising ahead of the little machine, and the encounter would change what we thought we knew, not just about Jupiter, but about what counts as a living, changing world. What Voyager found there, in the storms and around those 4 sparks of light, is where we drift next. Jupiter does not arrive all at once. It grows. For weeks in early 1979, Voyager 1's cameras watched the planet swell from a bright star into a world that filled the frame, and the closer it came, the stranger the familiar became. Through telescopes, Jupiter had always been a serene, banded marble, salmon and cream, with one famous red storm. Up close the serenity dissolved. The bands churned. They curled into each other along their edges in scrolls and feathers and slow whirlpools, like cream stirred into coffee by a very patient hand. The great red spot, a storm wider than the entire Earth, turned out to be only the largest member of an enormous weather system that never settles, never repeats. The spacecraft swept past its closest point to Jupiter on the 5th of March 1979, and in those few crowded days it gathered discoveries that textbooks still carry. It found that Jupiter has a ring, a thin, dark, almost invisible ring of fine dust, nothing like Saturn's bright bands, so faint that no telescope on Earth had ever caught it. The ring announced itself in a single long exposure Voyager took while looking back toward the Burr. Sun, the dust, lighting up the way motes light up in a low evening window. Astronomers had been looking at Jupiter for nearly 400 years, since Galileo first raised a telescope to it. The ring had been there the whole time, waiting for someone to stand on the far side of it. Voyager also found 2 small moons no one had ever seen, later named Thebe and Metis, little worlds only tens of miles across, circling close in against the giant. 2 more names added to the family. But the discovery people remember came from a world we already knew. Io, the innermost of Jupiter's 4 great moons, was expected to be a dead, cratered ball like our own moon. The pictures showed something else entirely. Io was smooth, young and strange, painted in sulphur yellows and oranges and whites. And then, in an image taken almost as an afterthought, looking back as the spacecraft departed, an engineer studying the pictures noticed a faint umbrella-shaped haze standing off the moon's edge. It was a volcanic eruption, caught in the act, a plume of material climbing dozens of miles off the surface, the first active volcano ever seen anywhere beyond Earth. Until that picture, every world we had ever visited was geologically quiet or geologically dead. Io was alive. It is, we now know, the most volcanically active body in the entire solar system, kneaded and heated from within by Jupiter's enormous tides. One photograph rewrote a basic assumption. Worlds did not have to be Earth to be alive in their own way. And beside Io swung Europa, pale and smooth and veined with long cracks. Like a frozen sea, Voyager's pictures of Europa were just sharp enough to be haunting. That cracked shell looked to many scientists like ice floating on something. The suspicion planted by those images that an ocean of liquid water might hide beneath would grow over the following decades into one of the most cherished ideas in science. And spacecraft are flying toward Europa right now, in our own time, largely because of what Voyager glimpsed in passing almost 50 years ago. There is something restful in that thought. A few days of photographs, taken by a machine moving too fast to stop, and humanity is still slowly unwrapping them half a century later. No moment of looking closely at the world is ever wasted. The understanding just takes its time arriving, like the signal itself. As Voyager 1 swung around the giant planet, Jupiter's gravity did what the planners had promised it would do back when the spacecraft was. Only pencil lines on paper. It took hold of the little machine and threw it. The spacecraft fell in toward the giants, sped up enormously, and was slung outward again on a new, faster path. Carrying borrowed momentum it would never give back. Jupiter, for its part, was slowed in its orbit by an amount so small that no instrument will ever measure it. The giant paid a toll it will never notice, and the traveller left richer. This was the trick that made the whole grand tour possible. Not bigger engines, borrowed strength. Each world passed would hand the spacecraft onward to the next, the way a parent swings a child between their hands. Behind it, Jupiter shrank week by week back into a bright star. Ahead lay another year and a half of falling, with the sun dimmer now, the signals home taking over an hour each way, and the next destination slowly brightening, Saturn, the ringed world, the jewel everyone was waiting for. But at Saturn, a quiet decision was waiting too, a choice the mission planners had made about Voyager 1's path, a choice about a single, haze-covered moon that would cost the spacecraft every planet that came after. Voyager 1 was about to make its final planetary visit, decades before its mission would end. Why they chose to spend the rest of the journey on one orange moon, and what that bargain bought, comes next. In November 1980, 3 years and 2 months out from Earth, Voyager 1 fell into the company of Saturn. If Jupiter overwhelmed, Saturn enchanted. The pictures coming home that month had a softness to them, bone and gold and pale honey tones, and around it all the rings. From Earth the rings looked like 2 or 3 solid hoops. Voyager saw the truth. They are thousands upon thousands of fine, distinct ringlets, grooves in a celestial record, each one a river of countless tumbling pieces of ice, from dust grains to drifting bergs the size of houses, all orbiting in a sheet so thin that, compared to its width, it is far thinner than a sheet of paper. Voyager 1 spent its days at Saturn the way it had at Jupiter. Gathering decades of science in a brief crowded passage, it found 5 new moons. It discovered a new ring called the G ring, faint and fine, It watched lightning-bright storms in the planet's quiet-looking clouds and measured winds near, the equator moving at over 1,000 miles per hour, 4 times anything Earth can produce, on a world that from a distance looks like stillness itself. The closest approach came on the 12th of November, 1980, but the planner's eyes were fixed on something smaller than the planet. Titan, Saturn's largest moon, bigger than the planet Mercury, and unlike every other moon known anywhere, Titan has a thick atmosphere, a deep orange haze that no telescope had ever seen through. In the late 1970s, scientists already suspected what that haze was hiding: a world with weather. A world with rain and rivers and seas, but built from a colder chemistry than ours, where the working fluid is not water but liquid methane at nearly 300 degrees below zero, a frozen mirror of the early Earth. And so the planners faced their quiet choice, made years earlier, and now coming due. The spacecraft's path could be bent to pass close to Titan, or saved for the planets beyond. It could not do both. A close Titan flyby meant Saturn's gravity would throw Voyager 1 up and out, away from the flat plane where all the planets live, on a path that led to no further worlds at all. Uranus and Neptune would be left for the twin, Voyager 2 trailing behind on its slower road. They chose Titan. That is how much one moon was worth. On the 12th of November, 1980, Voyager 1 skimmed within a few thousand miles of the orange haze and turned every instrument it had on the hidden world. The cameras, in one sense, were defeated. The haze never broke. No surface was ever seen. The pictures show a smooth amber sphere keeping its secrets, and there must have been some heartbreak in that. But the other instruments saw plenty. They measured an atmosphere mostly of nitrogen, like our own air, and denser than Earth's at the surface, the only moon anywhere with such a thing. They found the chemistry of organic molecules drifting in that haze, carbon compounds, the slow prebiotic kitchen of a world kept in cold storage. Titan turned out to be one of the most promising places in the solar system to study how the ingredients of life assemble themselves. A generation later, the Cassini mission and its lander Huygens would go back, pierce the haze, and find the methane lakes and rain-carved channels that Voyager's measurements had hinted at. The bargain paid off. It just paid slowly across decades to people who had been children when the choice was made. And then it was done. Saturn's gravity gathered up the little spacecraft and threw it, as planned, up and away, 35 degrees out of the plane of the planets northward into emptiness, on a path that no longer led anywhere at all. Voyager 1's planetary career ended that week, 3 years into a journey that has now lasted nearly 50. It is worth resting on that for a moment because there is something gently human in it. The spacecraft's most celebrated work was finished in its first 3 years. Everything since, the longest and in some ways the most profound part of its life, has happened after the part the world considered the main event. The camera's great subjects were gone. Ahead there was nothing to fly past ever again, just distance, deepening. The mission did not end, though. It transformed. The machine was renamed in spirit, if not in name. In January 1990, the project formally became the Voyager interstellar mission, and the goal was no longer any world. The goal was the edge. Somewhere far out there, invisible, the sun's influence had to end. The long exhalation of particles that streams off our star, the wind that inflates a vast bubble around the whole solar system. Somewhere that wind fails against the thin breath of all the other stars. Nobody knew how far away the wall was. The honest estimates disagreed by billions of miles. Voyager would simply keep flying until it hit it. But before the spacecraft gave itself fully to the dark, it had one piece of unfinished business, one last photograph. Not of anything ahead. There was nothing ahead. The cameras would be turned around against the engineer's instincts to look back the way it came. The picture it took that day in 1990 is, by many reckonings, the most important photograph in the history of photography, and taking it is the reason the cameras never saw anything again. That picture is next. By 1990, Voyager 1 was 3.7 billion miles from home, higher above the plane of the planets than anything had ever flown, and its cameras had been idle for 10 years. Space from out there is an almost featureless dark. One man kept asking for one more picture anyway. Carl Sagan had been part of the Voyager imaging team from the beginning. For years he had floated an idea that had no scientific justification at all, and he admitted as much freely. "Turn the cameras around," he said. "Point them back toward the sun. Take a portrait of the planets as seen from the outside, not for data. The planets would be barely more than grains of light. For perspective." The engineers resisted, and they had reasons. Pointing the cameras anywhere near the sun risked burning out their sensitive tubes, the way a child is warned not to stare at the sun through a magnifying lens. There were also costs. Every camera command meant time on the giant listening dishes of the deep space network, and competition for those dishes was fierce, and there was a schedule pressing in. The power budget said the cameras were living on borrowed time anyway. If the family portrait was ever going to happen, it had to happen soon. On the 14th of February 1990, Valentine's Day, the commands went out, and the old spacecraft began its last photo session. It swiveled its instrument platform back toward the inner solar system and worked through a careful mosaic, 60 frames in all, sweeping across the sky where the planets lay scattered around the small, pierce point of the sun. In one of those frames, partway up a soft ray of scattered sunlight, there is a speck. It is less than a single pixel across, pale blue. If you did not know to look for it, you would clean it off the image like dust. The ray of light it sits in is not even real, just sunlight scattering inside the camera, an artifact of optics pushed to their limit. By pure chance, the artifact fell across the speck like a spotlight. The speck is Earth, the whole of it. Everyone who has ever lived. Every sea and mountain and city and language, every war and every lullaby, caught from 3.7 billion miles away, suspended in a sunbeam that is not even really there. Sagan named the picture the pale blue dot, and a few years later he wrote the passage that fixed it permanently in human culture. "Look again at that dot," he wrote. "That is here. That is home." He asked his readers to think of all the generals and emperors who had fought to rule. For a moment, a fraction of that single point of light, he called Earth the only home we have ever known, a lonely speck in the great enveloping cosmic dark. The picture cost exactly what the engineers feared it would, and they paid willingly. Not long after the portrait was taken and slowly transmitted home, Voyager 1's cameras were shut down for good, to save power and computing for the instruments that could still do science in the dark, and the shutdown went deeper than a switch. In the years that followed, the camera software was deleted from the spacecraft's computers to free their tiny memories, and the equipment on Earth that knew how to read the camera data was retired and dispersed. The cameras can never be turned on again. It is not a matter of will or budget. The knowledge itself was let go. So the last thing Voyager 1 ever saw was us. There are sadder sentences in the history of exploration, but not many gentler ones. The spacecraft's eyes closed on a portrait of home, and everything since. The most distant travelling any machine has ever done has been done blind. It does not need to see where it is going. There is nothing to see. From now on, its remaining senses are the strange ones, the ones with no human equivalent, instruments that feel magnetic fields, instruments that count flying atoms, and two long whisker antennas that feel the faint trembling of the thin matter between the stars, which is the sense that this whole story has been quietly walking toward. It is worth saying clearly as you settle deeper into the dark of your own room what the spacecraft situation now became. After 1990, there was no destination anymore in any human sense. No arrival date, no world ahead. Mission planning documents stopped talking about encounters and started talking about boundaries, invisible ones whose distances were guesses. The spacecraft was now a swimmer far from shore, heading out, with instructions to report anything that changed in the water. For 8 more years it swam through the same solar sea, and then, in February 1998, came that quiet record we promised earlier. Voyager 1, on its faster heading, finally overtook the old Scout Pioneer 10 to become the most distant human-made object in existence, at 69 times the Earth-Sun distance. No bells rang on board. The two machines passed in absolute silence, too far apart to ever sense each other, two specks in an ocean. And the water stayed the same. Year after year, the same solar wind, the same slowly fading sun, the same patient falling outward. Until one December, deep in the darkness, the instruments stirred. Voyager 1 had found the first wall. To understand what Voyager struck in December 2004, it helps to lie back and picture the sun not as a light, but as a breath. The sun does not stay inside itself. It exhales constantly in every direction, a thin wind of charged particles, fragments of its own outer layers boiling off into space at hundreds of miles every second. This solar wind streams past Mercury, past Earth, where it brushes our magnetic field and lights the auroras, past Jupiter, past Saturn, past all the planets, thinning as it goes but never quite stopping. It inflates an enormous bubble in the galaxy, a region where the sun's breath dominates everything, and that bubble is called the heliosphere. Every planet, every moon, every human being who has ever lived has lived deep inside it. But the bubble cannot go on forever. The space between the stars is not truly empty. It holds its own thin fog of gas and dust, the interstellar medium, the mingled breath of all the other stars, and the slow ash of stars that died before the sun was born. Far out at some unknown distance, the pressure of the sun's fading wind and the pressure of that interstellar fog must come into balance. The theorists drew the wall in 3 layers, like the edge of a continent meeting the sea. First, far out, the solar wind would suddenly falter, dropping in an instant from supersonic speed to a slow, hot, crowded drift. The way river water piles up and slows where it meets the tide. That abrupt slowing they named the termination, shock. Beyond it lay a vast region of slowed, heated, turbulent solar wind, the heliosheath, the surf zone of the solar system, and at the outer edge of that, the true boundary, the heliopause, the surface where the sun's matter finally ends and interstellar matter begins. Past the heliopause, you are no longer swimming in anything that came from the sun. You are in the sea between the stars. That was the map. Nobody knew the distances, and only one machine was far enough out to find them, the honest way, by touch. Through the 1990s and early 2000s, Voyager 1 climbed through 70, 80, 90 times the Earth-Sun distance. The sun behind it dimmed to a fierce, bright star, casting less than a 10,000th of the light you feel on your face on a summer day. Out there, high noon is deep twilight. The spacecraft's plutonium heart kept it warm and awake while its instruments sifted the wind, year after year, alert for the first sign of slowing. In mid-December 2004, at 94 times the Earth-Sun distance, about 8.5 billion miles out, the sign came, The particle counts jumped. The magnetic field strengthened and grew rough. The character of the wind changed completely, from a clean, fast stream to a hot, dense, disordered crowd. Voyager 1 had crossed the termination shock. The sun's breath had broken its stride against the interstellar sea, and the spacecraft was through the first wall and into the surf. There is a lovely detail in how blunt the evidence was. The crossing itself happened in a gap between tracking sessions, the way so many of nature's thresholds slip past while no one is watching. But the water on the far side was unmistakably different water. The spacecraft woke up, so to speak, in the new country, and the instruments simply reported that everything had changed. For comparison, Voyager 2, on its slower southern road, would cross the same shock 3 years later, in 2007, at a noticeably smaller distance, 84 times the Earth-Sun span. The bubble, it turns out, is not a neat sphere. It is squashed and breathing, swelling and shrinking with the sun's moods, its walls flexing over billions of miles like the sides of a slow jellyfish. Now Voyager 1 was in the heliosheath, the surf zone, and the going became strange. The wind around it grew slower and hotter, and more confused with every passing year. The neat outward stream was gone, particles milled and eddied. Somewhere ahead, at a distance no one could agree on, the true edge was waiting. Some models said it was close, a few years' flight. Others said decades. Indifferent to the argument, made it steady 3.5 Earth-Sun distances of progress every year, the same pace it holds tonight. And here a quiet problem was waiting, one that would turn the most important crossing in the spacecraft's life into a year-long mystery. The instrument best suited to recognize the heliopause, the plasma sensor, the one designed to taste the density and speed of the surrounding matter directly, had failed back in 1980, all the way back at Saturn, decades earlier. It had never been repaired. There was no repairing it, which meant that when the moment finally came, when the old machine finally pushed its bow out of the sun's last thin breath and into the open, interstellar sea, the one gauge built to announce it would say nothing at all. The spacecraft would cross the most important boundary any machine has ever crossed, and not know. How the scientists finally found out, by argument, by accident, and by a kind of listening no one had planned, is the heart of this whole night. The year 2012 should have arrived with trumpets, and instead it arrived with a riddle. All through 2010 and 2011 the signs had been gathering that the edge was near. The outward flow of solar wind around Voyager 1 slowed, and then, strangely, stopped altogether. The spacecraft was 120 times the Earth-Sun distance out, in water that no longer moved. Mission scientists had spent their careers drawing maps of this frontier, and none of the maps had a region like this on them. The bubble's edge was not behaving like a wall, it was behaving like a wide, still margin, a place where the sun's breath did not so much end as lose its way. Then, in the summer of 2012, the deep space counters on board began to sing. Through July and August, the number of cosmic rays arriving from outside the bubble, fast particles flung across the galaxy by exploded stars, climbed sharply. At the same time, the particles native to our own bubble, the sun's particles, drained away. On the 25th of August, 2012, over the course of hours, both changes locked in and never reversed. The galaxy's particles flooded in. The sun's particles fell to almost nothing, as if a door had been opened and a draft had blown through the spacecraft's whole sky. By every particle measure, Voyager 1 had stepped outside. And yet the team could not bring themselves to say it, because one measurement refused to cooperate. The magnetic field, crossing into interstellar space, was expected to swing the direction of the magnetic field, around the spacecraft toward the galaxy's own alignment, and the field direction did not budge. The particles said outside, the field said inside, and the one instrument that could have settled it in an afternoon, the plasma sensor, the direct gauge of what the spacecraft was actually swimming in, had been dead for 32 years. So began one of the strangest years in the history of exploration. The most distant machine humanity has ever built had either left the solar bubble or it had not, and the people who knew it best could not agree which. Papers argued both sides. Press releases were drafted carefully and walked back, somewhere out in the dark. The spacecraft itself coasted on, perfectly indifferent, through whatever it was coasting through. What finally settled it was an accident of weather, solar weather. Back in March of 2012, before the crossing, the Sun had thrown one of its periodic tantrums. A great exhalation of material blasted outward from its surface. That blast wave spread out through the solar system, past the planets within days, and then kept going, slowing and fading, for more than a year, until in April 2013 its faint remnant finally rolled over the place where Voyager 1 now drifted, 13 months' travel from home shores even for a shockwave. And when it arrived, it did something wonderful. It rang the sea. The blast set the thin matter round the spacecraft vibrating, the way a passing truck sets a wine glass humming, and vibrating matter is exactly the thing Voyager's plasma wave antennas, those two long whiskers trailing behind, were built to feel. For the first time in 8 years, the whiskers reported tones. A clear, rising whistle in the data. A pitch. Here is the secret that turns the pitch into a depth sounding, and it is simple enough to fall asleep to. The thin matter of space rings at a frequency set by how crowded it is. Sparse matter rings low, dense matter rings high. The pitch is a head count, and the whistle Voyager heard was high. Far too high to be the Sun's sparse breath. The spacecraft was ringing with the dense, cold matter of the interstellar sea. It was floating in the wrong water for the inside of the bubble. It had been, evidently, for some time. The plasma wave team went back through their old data with new eyes, and there it was. Faint and overlooked, a softer whistle from October and November of 2012, at a slightly lower pitch. 2 soundings, 2 dates, 2 densities. They drew the line back, and it pointed cleanly at the doorstep. That day in late August 2012, when the particle counts had flipped. That had been the crossing all along. There was even a lovely independent check. Years earlier, an instrument team using sky maps from another spacecraft had estimated the boundary should lie at about 121 times the Earth-Sun distance. Voyager crossed at 121.6. The old map and the wet keel agreed within 0.5%. In September 2013, NASA made it official, a year late and certain at last. On August 25, 2012, Voyager 1 became the first human-made object to leave the heliosphere and enter interstellar space. Scientists on the team described literally jumping out of their seats when the whistles appeared. The magnetic field's stubborn refusal to turn remains a genuine puzzle to this day, a souvenir of how much subtler the real frontier was than anyone's drawing of it. But linger on the way, the answer actually came, because it is the quiet heart of tonight's story. The crossing was not announced by a camera or a beacon or a measurement anyone planned. It was announced by sound, by a ringing in the dark, struck by a storm that had left the Sun before the question was even asked. The spacecraft had ears all along, and once the scientists started listening, the sea between the stars turned out to have more to say. From here on, slow everything down a little more. The planets are decades behind. The story now is just a small machine, an ocean of almost nothing, and a faint set of sounds. You can let your eyes close for this part. Voyager would understand. Its own eyes have been closed since 1990. First, be reassured about one thing. because it puzzles everyone. Space is silent, that part is true. There is no air between the stars, and without air, there is nothing to carry the kind of pressure waves your ears were built for. If you floated beside Voyager and a bell rang against its hull, you would hear nothing at all. But silence is not the same as stillness. The space between the stars is filled, thinly, almost unimaginably thinly, with matter, cold gas, stray electrons, atoms stripped and drifting. In the region Voyager swims through, there are only a few dozen particles in a volume the size of a sugar cube, compared with the billions upon billions of billions in a cube of the air you are breathing. Now, it is a nearer perfect vacuum than any laboratory on Earth can make, and yet it is not nothing, and anything that is not nothing can tremble. When something disturbs that thin matter, a passing shock wave from the sun, a pressure front, the slow turbulence of the galaxy itself, the electrons in it are set swaying together, and they sway at a precise rhythm fixed by their crowding. These are the plasma waves we met in the last chapter. Voyager's two long antennas feel them directly, the way your skin feels a vibration your ears cannot catch. Beamed home and sped up, the recordings fall right into the range of human hearing. NASA has released them, and you can listen to them yourself. They are real sounds, in the honest sense that a recording of a whale is a real sound. The edge of the solar system, played back at human speed, whistles. That is what the title of tonight's episode means. In late 2012, 3 months after the quiet crossing, came the first interstellar whistle, the faint one nobody noticed at the time. In the spring of 2013 came the second, the loud, clear one that solved the mystery, and the two notes carried an extra message almost in passing. The second note was higher than the first. Higher means denser. In its first year at sea, Voyager was not drifting into emptier and emptier space, as you might expect with the sun falling ever farther behind. The water was thickening. That small rising interval, 2 notes a few months apart, was the first hint of a structure nobody had mapped. The interstellar sea is not uniform. It has shoals and currents, regions packed tighter and regions stretched thin, stirred over millions of years by exploded stars and the slow weather of the galaxy. The sun's bubble, it turns out, sits just offshore of denser water, and Voyager was wading out into it, taking the first soundings any creature from this solar system has ever taken. For a few years that was the whole method. Wait for the sun to throw one of its tantrums. Wait a year or more for the faded wave to roll over the spacecraft. Catch the brief ringing, read the pitch, mark the depth on the chart. Between tantrums nothing. The sea kept its own counsel, and the mission simply drifted and waited, sometimes for years between notes. The map of the interstellar shore was being drawn a single sounding at a time, by a machine running on the warmth of a fuel loaded the year disco was king. Each whistle lasted weeks or months, then faded, leaving silence again. Scientists assumed that silence was simply the truth of the place, an ocean that only speaks when struck. They were wrong about that, and the way they found out is one of the gentlest discoveries in modern astronomy. Years later, a young researcher decided to stop waiting for the loud moments, and instead gathered up all the quiet in between, every stretch of supposedly empty data the antennas had sent home from interstellar space, and laid it out end to end. Hidden in that quiet, faint beyond faint, at the very threshold of what the old instrument can feel, there was something, not a whistle, not an event at all. A tone, steady, narrow, patient. It had been there underneath everything, possibly the whole time. The sea between the stars, it turns out, does not only ring when struck. Left entirely alone in the deepest silence available to the universe, it hums. What that hum is, and what it is quietly teaching us, comes next. Stay with the sound. We are almost at the present day. In 2017, 5 years past the boundary, the antennas aboard Voyager 1 began registering a signal so faint that calling it a signal feels generous. It was less like a sound and more like a suspicion of one. Steady tone in the thin matter outside, right at the edge of the instrument's ability to feel anything at all. It went unremarked for years, buried in routine data, because everything about the mission had trained everyone to look for events. Shocks rolling in from the sun. This was the opposite of an event. It did not arrive, and it did not leave. It just continued month after month, a single drawn-out breath. The person who found it was not one of the mission's grey-haired founders, but a doctoral student at Cornell University named Stella Koch-Ocker, 3 generations younger than the spacecraft's first scientists, sifting through the old machine's data with fresh patience. She described what she found in the plainest possible words. "It is very faint and monotone," she said. "We are detecting the faint, persistent hum of interstellar gas." In May 2021, the discovery was published in Nature Astronomy, and it quietly rearranged how we get to know the sea between the stars. Remember what pitch means out there. The rhythm of the thin matter's trembling is a head count of its electrons. The whistles after solar storms have given soundings the way lightning gives you glimpses of a night landscape, brilliant and rare. The hum gives the same information continuously. It is as if, after years of waiting for lightning, someone noticed the landscape was very faintly glowing all along, just brightly enough to be read by a patient eye. A scientist on the team put it in words that are almost a lullaby in themselves. The spacecraft, he said, is continuously reporting, "Here is the density I am swimming through right now. And here it is now. And here it is now." 3 small wonders hide inside this discovery, and they are good ones to hold as you drift. The first is what the hum revealed about the sea itself. With a continuous sounding line instead of scattered storm glimpses, the team could trace the texture of the interstellar medium along 10 times the Earth's sun. Distance of Voyager's path, and the texture is gentle. The density rises and falls in long, soft swells, the wake of ancient turbulence, stirred by stars that exploded before the sun was born and never allowed to fully settle. Voyager is measuring the calm left over from catastrophes older than our world. There may be no better resume for a sleep story than that. The second wonder is what the hum probably is. The leading explanations are versions of the same humble idea, that this is the thermal murmur of the gas itself, electrons trembling simply because they are warmer than absolute stillness, the irreducible motion of matter that exists at all. Not a message, not a beacon, just the sound, if we may call it that, of the universe failing to be perfectly silent, the background texture of existence, caught by 2 50-year-old antennas at the limit of their hearing. And the third wonder is the instrument doing the catching. The plasma wave system listening for this faintest of all signals was designed in the early 1970s by engineers who never imagined interstellar service, and its lead scientist, Don Gurnett, who built wave instruments his whole long life, lived to see his Voyager antennas find the hum, the culmination listed alongside his name in the discovery, the student and the emeritus professor bracketing the spacecraft between them, 50 years apart, both leaning toward the same faint tone. Hold the whole picture for a moment, because this is the summit of the night, the thing the title promised. 15 billion miles from your bed, in water. No ship will touch again for generations. A machine from 1977 is floating in the dark, with its eyes long closed and its ears still open. Around it, the thin breath of dead stars is humming almost inaudibly. The way an empty house still ticks and settles in the night, the machine writes the hum down, patiently at the threshold of its old senses, and aims its dish at a pale blue speck it can no longer see, and sends the hum home, and 23.5 hours later someone on that speck reads it. That is happening now. It was happening an hour ago. It will be happening while you sleep. But the same arithmetic that makes this miracle run is also slowly ending it. The plutonium warmth that has kept Voyager's ears open for 50 years gives a little less every single year, and it cannot be refueled, and the mission has entered the long season of choosing what to switch off so that something may stay on. Before we sit with that ending, though, there is one more piece of cargo to visit, because Voyager is not only an instrument, it is also a letter, bolted to its side. Under a gold cover, there is a message addressed to whoever or whatever may someday drift alongside. The letter and the heartbeat pressed into it is next. In the spring of 1977, with the launch only months away, NASA handed Carl Sagan a strange commission. Both Voyagers would eventually leave the solar system entirely. They would outlive the mission, outlive the agency, outlive, in all probability, every structure standing on Earth. Should they carry something, a message in case anything ever found them? Sagan said yes, and gathered a small committee, and they gave themselves a task that no one had ever attempted with a straight face. Introduce Earth, all of it, to an audience about which nothing whatsoever is known, on a deadline of weeks. The form they chose was already a little old-fashioned in 1977, and that was part of its genius. A phonograph record, plated in gold, fitted into a protective aluminum jacket along with a cartridge and a needle, and engraved on its cover with careful symbolic diagrams a map of how to spin it, how fast, and how to turn the spiral groove back into pictures and sound. A record needs so little, no computer, no format, no electricity even, in principle. Just patience and the diagrams. The groove physically is the sound pressed into metal that in the vacuum of space will keep its shape for 1 billion years. It may be the most durable thing human beings have ever made. What they pressed into that groove in those few hurried weeks is worth listing slowly, because it is one of the loveliest inventories ever assembled. 115 images encoded into the record's tones, a page of mathematics, the structure of DNA, a mother nursing a child, traffic, houses, a string quartet, a man drinking water, the Earth itself photographed whole. The sounds of the planet gathered like specimens, surf against a shore, wind and thunder, birds, the songs of whales, rain, a heartbeat, footsteps, a baby crying and a mother soothing it. Then the greetings, 55 languages recorded mostly in a rush at Cornell University, ordinary speakers rather than statesmen, each saying some version of "Hello, peace, we wish you well." They arranged the languages across thousands of years of human time. The sequence begins in Akkadian, the tongue of ancient Mesopotamia, 6,000 years old, the language of the first cities humans ever built. It ends in Wu, a language of modern Shanghai. Between those two, the better part of everything we have ever said. And then 90 minutes of music, Bach 3 times, Beethoven, a pygmy girl's initiation song, Senegalese percussion, Japanese shakuhachi, a Peruvian wedding song, Mexican mariachi, Chuck Berry's Johnny B. Good, which drew some grumbling from classicists, and which the committee kept anyway, on the grounds that the Earth that launched Voyager was not only a planet of cathedrals, it was also a planet of garages. But the cargo that stays with people once they hear of it is none of these. While the record was being assembled, its creative director was a young writer named Andrew Yan. Her task list included finding a way to record the electrical activity of a human body, the heart, the brain, the nervous system, on the theory that a sufficiently advanced finder might one day read meaning back out of those signals. She volunteered herself, and in the days just before her recording session, something happened that no mission plan had scheduled. She and Carl Sagan, colleagues on the project, fell in love. A single phone call, by her own telling, turned from logistics into a life. They were engaged within days and stayed together until his death. So when she lay down in the laboratory, electrodes at her scalp and her chest, and let an hour of her body's quiet electricity be captured for the record, she was a woman newly, secretly in love, deliberately thinking as the machines listened, about what it is like to fall in love, about the history of ideas, about the human condition, about one particular human. The hour was compressed into a minute of sound and pressed into the gold. Played back, it sounds like a soft string of crackles and thuds. But that minute is, as literally as physics allows, the recorded inner weather of a person in love. It is on both Voyagers. It is the farthest any human feeling has ever travelled, and it is travelling still, about a light day out, getting a little farther while you fall asleep tonight. Sagan said of the whole project that the launching of this bottle into the cosmic ocean says something very hopeful about life on this planet. He also knew and said plainly that the bottle will almost certainly never be found. The galaxy is too large and too empty. 40,000 years from now the record will make its first faint approach to another star, and even then it will pass at a distance of more than a light year, a message in a bottle crossing an ocean with no far shore in sight. But found is not really the point of a message like this, is it? Some letters are written mostly for the sake of the writing. The record's truest audience may have been us, the people of the pale blue dot, who needed, in 1977 as now, the occasional reminder of what we sound like when we choose to introduce ourselves with music, and greetings and a heartbeat, instead of anything else. The letter is safe, it needs no power, and it will outlast the spacecraft carrying it by 1 billion years. The spacecraft itself is another matter. Its warmth is running out, and the long goodbye has already begun. We should sit with that now, gently, because it is gentler than you fear. Voyager 1 was never going to run out of fuel in the way a car does. Its ending was written into it before launch, in the physics of its power supply, and the writing is slow and exact. The spacecraft carries 3 radioisotope generators on a boom, finned metal cylinders that hold pellets of plutonium-238. The plutonium does nothing dramatic, it simply decays, atom by atom, and decay makes heat, and the generators turn that heat into electricity, no moving parts, nothing to jam or leak. It is the steadiest power source human beings know how to build, and it has run for very nearly 50 years without a day of interruption. But decay is itself a clock. Every year there is slightly less plutonium than the year before, and so slightly less heat, and so slightly less power. The loss is small and perfectly predictable, about 4 watts a year, year after year, the output of a nightlight, gone every 12 months. For decades that hardly mattered, the spacecraft had power to spare. By the 2020s, the engineers were describing the margins with the phrase razor thin. The mission entered the era of subtraction. Heaters were shut off one by one, including some protecting instruments that the textbooks said could not survive the cold, and which then went on working anyway, decades past their warranties, in temperatures their designers never signed up for. The old machine has repeatedly turned out to be tougher than its own paperwork. And then the subtraction reached the instruments themselves. Here is a thing about this mission that deserves to be more famous than it is. The choosing of what dies first was not done in crisis in some tense overnight meeting. It was done years in advance, calmly, by the scientists and engineers together, sitting down and agreeing on the order in which the spacecraft's senses would be given up. so that when each moment came it would arrive as a plan and not as a grief. There is a written sequence, a quiet pre-agreed order of lights going out, designed around a single goal, that at least one instrument should still be feeling the interstellar sea into the 2030s. The sequence is well underway. Of the 10 instrument sets each Voyager launched with, 7 have now fallen silent, some long ago, the cameras among them, and the pace has quickened in just the last 2 years. In October 2024, Voyager 2's plasma sensor was switched off. In February 2025, Voyager 1 gave up its cosmic ray subsystem, the very instrument whose counts had announced the 2012 crossing. A month later, Voyager 2's particle instrument followed. And then, in April 2026, only weeks ago as this story is being told, came the latest and hardest subtraction. Engineers at a Jet Propulsion Laboratory transmitted the command to shut down Voyager 1's low, energy-charged particle experiment, an instrument that had run almost without interruption since 1977, 49 years of continuous duty. The command itself took 23 hours to crawl out to the spacecraft at the speed of light, and the shutdown sequence took 3 more hours to complete, the instrument's last day longer than some missions. One detail from that day is almost unbearably tender. The instrument includes a small motor that turns its sensor head in a slow circle, so it can scan the whole sky. The motor was tested back in the 1970s to 500,000 steps. It has performed more than 8 million, and when the instrument was powered down in April, the engineers chose to leave that little motor running. It costs half a watt. Keeping it turning keeps the mechanism from freezing solid, which keeps alive the possibility, however small, that the instrument might one day be switched back on, a half watt of hope spinning in the dark. What remains awake on Voyager 1 tonight is exactly 2 senses. The magnetometer, which feels the faint magnetic field of the interstellar sea, and the plasma wave system, the whiskers, the ears. Of everything the spacecraft has carried, the ears are among the last to close. The instrument that heard the whistles at the crossing, the instrument that caught the hum underneath everything, is still on duty tonight, which means the title of this episode is not really in the past tense after all. What Voyager heard at the edge of the solar system, it is hearing now while you drift. The arithmetic ahead is not complicated, and we will not pretend otherwise. 4 fewer watts every year, 2 instruments left, and a body of engineering already running on margins thinner than any backup plan. Each spring, roughly, brings another decision. Of keeping some science alive into the early 2030s, and of the spacecraft's 50-year flight already standing as something no one designed, and no, one will soon repeat. But this particular spring brought something else as well, not a subtraction for once. A scheme. The engineers studying the power budget found one last card to play, an idea they nicknamed with a grin. And if it works, a dead instrument might actually be brought back from the quiet. The mission that has spent 2 years saying goodbye may be about to take one small thing back. That unfinished gamble happening right now in our own months is where we go next. Engineers who have nursed one machine for half a century develop a particular kind of imagination. Nothing on Voyager can be repaired. Nothing can be replaced. Every solution has to be found inside what is already there, 15 billion miles away, using only words sent by radio. And the team has pulled off enough of these rescues over the decades that each new crisis is met less with despair than with a kind of craftsman's squint. In February 2026, Voyager 1 gave them a scare. During a routine roll maneuver, a planned slow rotation the spacecraft performs to keep its instruments calibrated. The power draw dipped unexpectedly, nothing failed, but on a craft running this close to its margins, an unexpected dip is a serious letter from the future. If the supply ever sags below a hard threshold, An automatic protection system seizes control and starts shutting things down on its own, by a code logic written into it decades ago, with no regard for any scientist's careful list. The team would then face weeks of delicate recovery, conducted by messages that take a day to arrive and a day to answer. The April shutdown of the particle instrument was, in part, the response to that letter. Buy back the margin. Keep the old protections asleep. But alongside the subtraction, the engineers had been working out something more ambitious. The details are technical, but the spirit of it is simple, and the spirit is the part worth carrying towards sleep. After studying their 50-year-old power system, the team concluded that there was a way to squeeze one more useful measure of capacity out of it, a reconfiguration no one had ever needed to try in all the mission's decades. Engineers being engineers, the scheme acquired a nickname with some swagger in it. They call it the Big Bang. And the plan for deploying it tells you everything about how this team thinks. They will not try it first on Voyager 1. Voyager 1 is the treasure, the farthest thing, irreplaceable in the strictest meaning of the word, so the experiment goes first to the twin. Voyager 2 has slightly more power in reserve and sits 4 billion miles closer, and so it becomes, in its sister's service, the test subject. The trials were scheduled for May and June of 2026, which is to say, they're happening now. As these words are being read to you, somewhere between this room and the edge of everything, a 50-year-old spacecraft is trying an experiment its builders never imagined, so that its twin might keep one more sense alive a little longer. If the trials go well, the team will attempt the same fix on Voyager 1, no sooner than July, and if it works there, they have said something remarkable. There may be enough margin to turn the April instrument back on. The little motor, remember, was left spinning for exactly this reason. The lights on this spacecraft have only ever gone out. There is a real chance, this very summer, that for the first time in the long subtraction, one comes back. No one knows yet how it ends. We are telling you this story from inside it. That is rare in astronomy, where most stories finished millions of years before anyone heard them, and it seems right that you should know tonight's story is still being written a light day away. Sooner or later, of course, the large arithmetic wins. It is worth knowing, gently, what the actual end will probably look like, because it is nothing like the endings we are used to. There will be no crash. There is nothing to crash into, and will not be for tens of thousands of years. There will be no explosion, no falling from the sky. No one will switch Voyager off either. The team has been clear that they intend to listen for as long as the faintest signal remains. The end, when it comes, will be one of a few quiet failures, and the engineers can name them like old acquaintances. Perhaps the fuel lines that feed the little attitude thrusters will finally freeze in the deepening cold of the underpowered craft, and the spacecraft will slowly lose its aim, and the great dish will drift away from the pale blue dot it has pointed at for 50 years, and the Whisper will simply wander off into the dark, still being sent, no longer arriving. Perhaps the power will at last sag below the threshold from which nothing returns. Perhaps some single component, older than most people now living, will quietly decline to wake one morning. On Earth. On that day, whenever it comes, a dish the size of a building will be listening, and will hear nothing, and the operators will try again and again for weeks, because this team does not give up easily, and then at some point a person not yet known, on a date not yet set, will be the last human being ever to have heard from Voyager 1. And here is the strange consolation, the one the engineers themselves reach for. Nothing about the spacecraft's journey will end that day. Silence is not stopping. The craft will go on at exactly 17 kilometers every second, perfectly aimed by nothing at all, holding its course without any need of us. The record still bolted to its side. The mission ends. The voyage does not. where that voyage goes after the last whisper, across the next 40,000 years and beyond, is the last thing we will follow tonight. It is the deepest water of all, and the calmest. Tonight, while you have been listening, Voyager 1 has travelled about 60,000 miles. It is now roughly 170 times farther from the Sun than the Earth is, around 15 billion miles out, and every year adds 3.5 Earth-Sun distances more. The numbers are beyond holding, so hold this one instead. Sometime in the middle of November 2026, just months from now, Voyager 1 will become the first human-made object in history to reach one full light day from home. A signal leaving Earth that morning will arrive at the spacecraft a complete day later. We are about to have sent something a day away. And yet, in the geography of the galaxy, the journey has barely left the front garden. The Sun's gravity does not end at the heliopause. Far beyond the bubble of solar wind lies the Oort cloud, a vast, sparse shell of icy bodies, the deep frozen leftovers of the solar system's construction, drifting in orbits so wide they take millions of years. It begins, by current estimates, hundreds of Earth-Sun distances out, and stretches perhaps 1,000 times farther still. Voyager 1, the fastest long-distance traveller we have ever built, will not reach the inner edge of the Oort cloud for about 300 years. It will then spend on the order of 30,000 years passing through it, 30,000 years of our descendants' history, all of it unfolding while our little machine is still, technically, leaving home. The plutonium will be long cold by then. The generators that have warmed the spacecraft for 50 years will fade below usefulness in the 2030s, and below everything not long after, and from then on Voyager will make the crossing dark and silent and unimaginably cold, a few degrees above the temperature of space itself. Nothing about that harms it. Nothing out there touches it at all. A speck of dust striking once in a long while, starlight too faint to warm a coin. The vacuum between the stars is the most protective museum case there is. The craft will simply persist, gold record intact, aimed nowhere in particular, falling forever through the quietest territory that exists. In about 40,000 years, the first milestone of the long dark, Voyager 1 will drift within less than 2 light-years of a small, dim red star called Gliese 445. Notice the careful words. Within 2 light-years, that is the close approach. 11,000 times the distance between the Earth and the Sun, a pass so wide that from the spacecraft the star will be nothing more than another point of light, slightly brighter for a few thousand years, then slowly fading again. The spacecraft is not aimed at any star. It will never arrive anywhere. Arrival was only ever a planetary habit, and Voyager has left the country of planets for good. Its twin has its own appointment, passing at a similar distance from a star called Ross 248, in roughly the same era. The two machines, by then separated by a gulf wider than anything in human reckoning, will keep their separate courses around the galaxy from then on. 2 grains of 1977 circling with the stars, completing an orbit of the Milky Way every 250 million years. And the record will still be readable. That is not poetry, it is materials science. Gold does not rust, and space does not weather. The engineer's sober estimate is that the records will remain playable for 1 billion years. More. 1 billion years ago, the most complex living things on Earth were single cells. On those time scales, the record is not a message from a civilization. It is a fossil of one, perhaps eventually the only one, long after the Sun has swollen and taken the inner planets. After every monument and every backup of every archive is gone, the farthest surviving trace of what we were may be a gold disc sailing in the dark, carrying 55 greetings, a string quartet, the sound of rain, and 1 minute of the heartbeat of a woman in love. She knew, by the way, Andrew Leon was asked many times in her long life, Whether it troubled her that the message would almost certainly never be found, she always said some version of the same thing. That was never what it was for. So let us put you to bed with the picture as it stands tonight, because every word of it is current and true and happening while your eyes are closed. 15 billion miles from your pillow, a machine older than most of the people operating it, is falling outward through the hum of the interstellar sea. Its eyes have been closed for 36 years. Its ears are still open. Twice a year or so, it is asked to give up another piece of itself. And it does, and keeps going. This very summer, its twin is testing a trick that might briefly turn one light back on. In November, it will be one full day away at the speed of light, and after that it will just keep being farther every single moment, for longer than the Earth itself will last. It is the quietest story we know, and it has no ending, only distance. Next week on the Slow Cosmos, we stay out in the deep water with a harder question. Voyager told us where the sun's bubble ends. It could not tell us why the bubble is shaped so strangely, why the wall refused to behave when we finally touched it, or what is pressing on it from outside. Something is. The next episode is about the shape of the shore we live behind, and the weather of the galaxy beyond it. Until then, the dish is still pointed home. The hum is still arriving. You can sleep. Somebody very far away is keeping the watch.